Hello, ladies and gentlemen. Mr. Dorfler here for the completion of section 5, I believe it is, of our notes looking at how we determine empirical formulas. Now, I'm going to try to make this video as short as I can because I know there are some people out there who just don't want to listen to me for an entire day. I don't know. I'm as shocked as most of you are. I mean, I could listen to myself talk all day. But whatever time it takes is the time it takes, okay? Because there's a few things that we've got to get through today so that we can move on to the next section next week. So, yesterday, we began our journey into calculating empirical formulas. And I think we did that pretty well. Then we got into how we determine molecular formulas, okay? Now we're going to combine those two because we all left off, every class left off at this practice exercise here. So before we get started, this is what you're going to need to know and have for today's lesson. Your notes, your flowchart number 2 that I gave, or the one that's also found in your notes for those of you who are at home, calculator, and scrap piece of paper if you want some more room, because we're going to be doing lots of mathing today. Lots of mathing. After we get done with this, we then get into combustion analysis. And I have kind of come up with a flow chart of my own. In fact, combustion analysis actually takes 2 flow charts to complete. So you're just going to have to follow along with me as we make this journey together. Anyway, let's get back to the practice here. 314 or 3.14. And it says ethylene glycol, which is used as automobile antifreeze, is 38.7% carbon, 9.7% hydrogen, and 51.6% oxygen by mass. Its molar mass is 62.1 grams per mole. We're going to come back to that number in part B. So the first part is we have to figure out what the empirical formula of ethylene glycol is before we can even go and do part B, which is determine the molecular formula. So we have to go to our flow chart. And I'm going to exit out of here. And since we know what percentages each one of the elements is, take a quick, memory and ask yourself, okay, what does that mean? What does that tell us if we know what percentage it is? Okay, where do we start on the flow chart? Well, we would start on the very left of the flow chart here. Okay, so we're going to start here. And we're going to assume that we have a 100 gram sample. And so what that means is that for carbon, we have, where are we? 38.7 grams. For hydrogen, we've got 9.7 grams. And for oxygen, we have 51.6 grams. Okay? And so, according to our step, that gets us to right here. So, if we do our little calculating here, we have to go from grams to moles, and we're going to use the molar mass. So, again, mole is going to be on top for each one of these. Okay, and we refer to the periodic table. Carbon is going to be 12 grams. Hydrogen is going to be 1 gram. And oxygen is going to be 16 grams. So we'll go ahead and multiply it. At any point of this video, feel free to, pause the videos, do your own calculations, and restart the videos to check as you need to. Okay? All right, so when we calculate the number of moles of carbon, we get 3.23 moles. For hydrogen, we get 9.7 moles. And for oxygen, we get 3.23 mole. All right. So that gives us to this step. We now have moles of each element. Our last step is to determine the mole ratio. So remind yourself, how do I do that? Well, you find and determine the smallest number of moles and divide all of them by that smallest number. Now, in this instance, carbon and oxygen just happen to be the same. So we're going to choose, doesn't matter which one we choose because we're actually only choosing the number, not the element itself. And so we divide each one by the smallest mole amount. Okay? And then, remember, we when we calculate this, we want to make sure that they are within the experimental error. And so we're going to get a 3 for the hydrogen and 1s for the carbon and oxygens. Now, going back into what I said yesterday, and when you finalize your formula, you always look back at the question and place your elements in the order in which you came across them. So we first came in order of carbon, then we went to hydrogen, then we went to oxygen. Okay? So, again, we don't ever put a subscript of 1 on an element in a formula. So our formula, I'm going to actually clean this up a little bit, is going to be so that's not 4, CH3O. Okay? So empirical formula, I'm just going to call this EF, is CH3O. The next thing we need to do is go back into the problem, and we have to solve our part B, which was the molecular formula. So remember, we have to get the whole number multiple, and we get that by taking the, essentially the molar mass or the experimentally found molar mass of the compound itself and divide it by the empirical formula weight. And so we were told in the problem, and you can go back to it if you want to, but we were told that the molar mass of the formula itself was 62.1 grams per mole, or sorry, AMU. I should say molecular weight, not molar mass, okay, because they're different units. And if we calculate CH3O, okay, like we've done before, we've got 1 carbon, 3 hydrogens, and 1 oxygen. 12 is for carbon, 1 is for hydrogen, and 16 is for oxygen. You multiply, then sum all those up, you should get 31. Okay? And so you take 62.1 divided by 31, and you should get a whole number multiple of 2. So you take this whole number multiple of 2, multiply it by all subscripts, whether they're listed or not. And so we get a molecular formula of C2H6O2. That is the answer to part B. And I mentioned yesterday that we can always check to make sure that this is correct by calculating ourselves the molecular weight of our molecular formula. So again, just showing you how to do that. We've got 2 carbons now. We've got 6 hydrogens, and we've got 2 oxygens now. So go ahead and calculate this. 24 plus 6 plus 32. That's 24 plus 6 is equal to 30 plus 32. We get 62, which is pretty much on the money there. So we are good. Okay? Whew. So that is how we determine the empirical formula, which is CH3O. And the molecular formula for part B is C2H6O2. All right. Now comes the fun part. I'm going to erase this. I'm going to be taking up a lot of space at this next one here. Okay, I'm not going to sugarcoat it. So, getting back into the notes. Oh, I forgot to change the lighting. Okay, that's all right. All right. Getting into combustion analysis. Okay. typically, when we have a combustion analysis or just combustion in general, the sample substance that we are going to combust is typically going to contain carbon and hydrogen, at least. Sometimes they even contain oxygen. But when we analyze these substances, we need to be able to determine what molecular formulas are present in those substances. And so we use what's called combustion analysis. So we have a sample that is combusted, again, typically a hydrocarbon, and O2 is always going to be present whenever we have a combustion because it requires oxygen to essentially ignite. Anytime there's a combustion reaction, we're going to have the products H2O in the vapor form and CO2 gas every time. So we collect in these two absorbers, the H2O in the H2 absorber and the CO2 in the CO2 absorber. We then measure the masses of the H2O and the CO2 that were collected, and that starts our analysis. And so basically what we have to do is we have to take the H2O and the CO2 and break those down to help us determine the number of carbons, or the mass of carbon present, the mass of hydrogen, and the mass of oxygen. Okay, so I have kind of developed my what I call my part one of the problem, the part one flow chart for combustion analysis. I'm going to do that here in just a second. But where do we find the mass of carbons, hydrogen, and oxygen from CO2 and H2O? Well, carbon will be determined by the mass of CO2, hydrogen by the mass of H2O, and oxygen can only be solved after carbon and hydrogen have been found, because that's going to essentially be the difference of the mass of carbon and hydrogen from the original sample size. Okay, so first thing before we get into this, I want to show you what my steps are for part one, going from CO2 or H2O to carbon and hydrogen. So I'm just going to do this in one. I'm not going to do one specifically for carbon and one specifically for hydrogen. They're just going to be in one. Okay, so you might be good to write this down. Okay, so the first thing is we will be given the mass of CO2 and H2O. Okay, so this is like our first block. We then need to go to use the molar mass of CO2 or H2O. So 1 mole of, actually, I'm going to erase this. Sorry, erase. We need to get to moles of CO2 and H2O. Okay. And I'm going to come back also to include how we do this. Okay. We then need to get to mole of carbon or hydrogen. And lastly, our last step is going to be the mass of carbon and hydrogen. Okay, so 4 steps. Go from mass of CO2 or H2O to the moles of both, to the moles of carbon and hydrogen, and the mass of carbon and hydrogen. So in this step here, you are going to use molar mass of CO2/H2O. Okay, that's step 1. To go from moles of CO2 and H2O to moles of carbon and hydrogen, you are going to use the mole ratio. So, if you're finding for carbon, you're going to refer back to how many carbons are in a mole of CO2. So how many moles of carbon are going to be in a mole of CO2? So you have to look at the subscripts. All right. And then lastly, step 3, we are going to use the elements molar mass. Okay, so there you have it. That is my part one, or number one, flowchart for combustion analysis. So make sure you get that jotted down. That's going to help you in your problem set, in these practice exercises, and your final super quiz that's coming up here in a little over a week. Okay? So again, this is the flowchart. It's proprietary. It is not in any textbooks that I know of. I made it up myself. All right. So if you need to pause it to write this down, then pause it. But I'm going to clean this off and get started. Let's see. Let's lighten up the mood here. There we go. Let's get back into it. All right. So we are hopping right into the problem here. So we have isopropyl alcohol. Let me get my little pointer here. Isopropyl alcohol, which is sold as rubbing alcohol. It's also the alcohol that is used to clean off the Chromebooks during this pandemic. Anyway, it is composed of carbon, hydrogen, and oxygen. The combustion of 0.255 grams, now that's important. This 0.255 grams, that is our sample size. We gonna need that here in a little bit, okay? So the combustion of 0.255 grams of isopropyl alcohol produces 0.561 grams of CO2 and 0.306 grams of H2O. We are to determine the empirical formula of isopropyl alcohol. Okay, now, before we get started into the calculations and discussing the calculations, I just gave you part one flowchart for combustion analysis. Once you have determined the masses of carbon, hydrogen, and oxygen, you then go into the flowchart for empirical formulas. So again, there's two flowcharts that are necessary for combustion analysis. That's why I wrote down that first one, because it is muy importante. So let's begin. So according to flowchart number one that I just gave you, you have got to put down what you're given, okay? The mass of CO2 and the mass of H2O. You have to solve these individually, unfortunately, okay? So in order to solve for grams of carbon, you have to first go through CO2. You take your given of 0.561 grams of CO2, okay? Then you have to get to step two, which is the moles of CO2. And you use the molar mass of CO2, which is 44 grams per mole. Grams cancel. Moles are on top. So now you have moles of CO2. The next step is to get to moles of carbon, which you have to use the mole ratio, which simply just says, look at the formula, okay? If we have 1 mole of carbon dioxide and there's only 1 carbon in a single molecule, so that's a 1-to-1. 1 mole of carbon in 1 mole of CO2. That's why back when we first started talking about moles and everything that was associated with it, I went over how we separate and determine how many of the individual elements of a molecule will be determined, how many moles will be present, okay? It's all based upon the subscripts. So then we get the moles of CO2 can cancel. We are now in the step 3 where we have moles of carbon. And the final step, to calculate the grams of carbon, we take the molar mass of carbon, making sure grams is on top because that's what we need in our final answer. And we multiply all those through. So 0.561 divided by 44 times 1 times 12.0. And we find that we have collected 0.153 grams of carbon. This whole process also goes back to the law of conservation of matter. What was present at the start of a reaction must be present and accounted for after the reaction has occurred. So all of our masses need to add up and be present. Okay, maybe talking a little fast, but there's just so much, okay? So we have now calculated the grams of carbon. We then need to calculate the grams of hydrogen, and we follow the same steps that we just did in carbon. We start off with our given in grams of H2O. 0.306. We then need to go from grams of H2O to moles of H2O. So we use the molar mass of water. 1 mole on top, 18 grams of H2O on bottom. Grams cancel out. We now have moles of H2O. We need to get to moles of hydrogen. And looking at the formula, has a subscript of 2. So there are 2 moles of hydrogen per 1 mole of H2O. Now we have the number of moles of hydrogen through the mole ratio, and now we need to figure out the grams of hydrogen, and we do that by multiplying the molar mass found on the periodic table, do all the necessary calculations, and we find that we have 0.0343 grams of hydrogen. Okay. So now the question is, now that we've figured out grams of carbon and hydrogen, we were told that we have oxygen present. Oxygen is also in the formula. So we need to figure out the number of grams of oxygen that is also going to be present. Well, oxygen was present in both CO2 and H2O. So that's why it has to be sitting there till last to be found. So what we need to do is we need to add the mass of carbon and the mass of hydrogen and subtract that sum from our initial sample size, which I said was going to be very important, okay, of 0.255 grams. And we find that we have 0.068 grams of oxygen. Okay, so we have finally determined the mass of grams of all 3 components. And if we were to sum up all 3 masses of the components, we get the total sample size that we started with, which is good. We're following the rules of nature. Okay. Take a breath. Now that we have the mass in grams of all 3 components, we can then go into yesterday's flowchart. Okay? We go from mass, we don't even have, well, we can skip the mass percentage step, okay? We don't need to do that. We are starting at the gram step. So then we are here, we go to the moles of each element. So we have to use the molar mass. So we take the mass that we determined for each one and multiply it by their molar mass, making sure moles is on top because that's what we're solving for. Once we have calculated the number of moles for each element, we then identify who is the smallest. In this case, it will be oxygen. So we take all of these numbers and divide it by the smallest number of moles. And so then we get our whole number ratios. Well, except this one. But this one's close enough to attribute to experimental error, so we can just round up to 8. So we get C3H8 and oxygen 1. So therefore, we get the empirical formula of C3H8O as we see here. So C3H8O is the empirical formula of isopropyl alcohol. Now, that could also be our molecular formula, but we wouldn't know unless we were given some additional information. But we're not asked to solve for molecular formula right now for isopropyl alcohol. We were just asked to figure out empirical. We could determine molecular, but we're not going to right now. Now comes our turn. Okay? So, Ollie G. Okay. Let's look at our example here. Caproic acid, okay, we're right here, which is responsible for the odor of dirty socks, is composed of, wouldn't you guess it, carbon, hydrogen, and oxygen atoms. Combustion of 225 gram sample of this compound produces 0.512 grams of CO2 and 0.209 grams of H2O. A, what is the empirical formula of caproic acid? And B, if caproic acid has a molar mass of 116 grams per mole, we could also say a molecular weight of 116 AMU, what is its molecular formula? So we get to do the long haul here, people. All right. So let's start off with flowchart number 1 in CO2. Okay, we have to determine the number of grams of carbon and the number of grams of hydrogen and the number of grams of oxygen. So I'm going to have to fix my camera and dim the lighting. Okay, so in order to solve for grams of carbon, I'm going to try to write somewhat small, but still legible for us to read it. According to that flowchart that I told you to write, we write down our given, okay? And we were told that we have 0.512 grams of CO2, okay? We then need to go from grams of CO2 to moles of CO2 by using the molar mass. And what's nice about this, people, what's nice about this, and I'm upside down, but the molar mass of carbon dioxide and water is not going to change. So there's really only a few changes that you have to do, and that is the mass that is given of CO2. Everything else from this point on is constant. The molar mass or the mole ratio of carbon to CO2 is the same. The molar mass of carbon is the same. Okay, so it should become somewhat habit, or I just lost the word I wanted to use. I can't think of it. Should be a form of habit for us whenever we get to this point. So we have 44 grams. Okay, that gives us to moles of CO2. We then have to get to moles of carbon using the mole ratio. Again, there's 1 mole of carbon for every 1 mole of CO2 because we look at the subscripts here. And then we have to determine the grams of carbon by using the molar mass of carbon, which is 12 grams per 1 mole. Okay? So again, this all stays the same for carbon dioxide and carbon. The next one's going to stay the same for hydrogen and H2O. This is the only thing that changes, the given mass. Can't stress that enough. Okay? So when we go ahead and do our mathing here, take 0.512 divided by 44 times 1 times 12, we get 0.140 grams of carbon. Okay? 0.140 grams of carbon. So I've got that so far. Next, I need to calculate the grams of hydrogen. And I follow the same pattern. My given in grams, 0.209 grams of H2O. We then have to determine the number of moles of H2O. Again, this is where it all becomes the same. 1 mole over 18 grams of H2O. Then, to get to, we use the mole ratio of hydrogen to H2O. Okay, so in 1 mole of H2O, there are 2 hydrogens present in 1 mole, so we have to take 1 mole times 2. We get 2 moles of hydrogen. We then need to figure out the number of grams of hydrogen present through the molar mass, which is 1.01 grams. Again, you can use 1.0 if you want to, of hydrogen per 1 mole. So 0.209 divided by 18 times 2 times 1. We get 0.0235 grams of hydrogen. Okay? So we have our mass of carbon and our mass of hydrogen. We now have to sum those up and subtract it from our total sample mass that we were given in the problem to help determine the mass of oxygen. So our total sample size was 0.225 grams. And from that, we're going to subtract the sum of 0.14 and 0.0235. And so the mass of oxygen will be 0.062 grams of oxygen. So we now have our mass of carbon, our mass of hydrogen, and lastly, our mass of oxygen. Okay, if you need to pause now, because we are now done with this part 1 of combustion analysis, okay? I know, this is part 1 of A. We still have to do part 2 of A and then do B. So this takes up a lot of room. So I'm going to erase this. If you need to pause, I'm going to do a slow kind of movement of this just so you can see all of my numbers here and pause anytime you need to. I'm going to erase this. Because now that we know the mass of all 3 of those, we then have to go into our flow chart from yesterday, the empirical formula flow chart. We do not need to worry about the mass percent of the elements. We already know the grams. So we need to go from, again, we bring this out here, grams to moles to the empirical formula. So grams through molar mass to moles, and moles through mole ratio to empirical formula. So let's start off with moles of carbon, moles of hydrogen, and moles of oxygen. So in terms of moles of carbon, we calculated in the first part that we have 0.14 grams of carbon. We then use the molar mass of carbon, which is 12 grams, and we get 0.012 moles of carbon. Do the same thing for hydrogen. Hydrogen, we had 0.0235 grams of hydrogen multiplied by its molar mass of 1 mole per 1 gram. And we get, or if you did, I'm gonna put what I put here. You could do 1 mole, okay? You might get something slightly different, but it won't make a difference. So 1 mole over 1.01 grams of hydrogen. And that gives us 0.0233 mole of hydrogen. And then lastly, mole of oxygen. We calculated at the very end that we had 0.062 grams of oxygen. Multiply by, or divide, however you want to say it, by its molar mass of 16 grams. You get 0.0039 mole of oxygen. Okay. We now have our moles of each element. So again, ask yourself, what do we do? Well, we have to identify who the smallest number of moles is. And that, again, is oxygen. So you're going to take all 3 of these and divide it by 0.0039. Okay? And this for oxygen is just going to be 1. For carbon, it's going to be 3. And for hydrogen, it's going to be 6. So that gives us the subscripts for our empirical formula of C3H6O. That is your answer for part 1. Okay, I gotta move my camera just a little bit. So now that we have part 1 answered, or part A, part B, we need to figure out the molecular formula. Okay, we were told that the molar mass, or we can also say molecular weight, of caproic acid that they're using has a mass of 116 grams per mole, or you could do AMU, it doesn't matter, because really they're going to cancel out anyway. So we have to figure out, first off, we have to figure out the formula weight for the empirical formula. So we have 3 carbons, we have 6 hydrogens, and 1 oxygen. We sum those up, and we get 58. Okay, you can write AMU if you want to. So we have to figure out a whole number multiple. whole number. Again, that is going to be the actual molar mass of the compound divided by the empirical weight. So 116 divided by 58, we get a whole number multiple of 2. So now, in order to answer for B, we have to take the whole number multiple of 2 and multiply all subscripts by that whole number multiple. So part B, we get a final answer of C6H12O2. Again, if we wanted to, we could check it, but we're good. Okay? We are good to go on that. So this is part B. This is the molecular formula. This is the empirical formula. And that, folks, is all she has for combustion analysis. Only took a little bit of time, okay? Which is kind of why I'm happy that our super quiz that's going to have, I think at least one of these on there, you're not going to have a time limit, okay? You're going to have a due date, but not a time limit, so you can work through these at your own pace. So as you see, it takes a lot of space, okay? A lot of space. Just in my notebook alone, this one problem, it took up an entire sheet, okay? And not really a whole lot of space in between everything. So make sure you have enough paper to go around. That gets us through section 5. Yay, now we only have like 2 sections left to go. Next week, again, pay careful attention to Classroom because I will be posting at least one video on the lab that we were going to do, but with everything going on, we're going to have to skip this year, at least in person. It's a really great lab. I don't want you to miss out on it, so be looking for that. And just keep an eye on Planbook and Classroom for any future posts. But until then, I hope you have a great rest of your day, great weekend, great holiday. I will see all of you later. Bye-bye.